Yes. So, right, injective modules. I is an injective module if given an injection. So A to B. So I'll just stick the 0 in here as well. Maybe it's here. I don't know. I should name this, let's say alpha. There exists a map. Oh. No. This should be F, yeah. And a map A to I. There exists a map beta going from B to I such that, so the picture that I'm going to draw is very similar to the one for projective modules, but flipped around, right? So 0, A, B. This map is F. Then going into, no, not into, but out of, right? It's flipped. Out of A and into I is alpha. We have, it's this lifting thing again. You can connect B and I together with the map beta that makes this commute. So alpha is equal to beta F, right? Yeah, F and then beta. Yeah. And so historically, people actually thought about injective modules first before they did projective modules. Okay. And so, like before, we should expect like a similar result as last time. So the following are equivalent. So B is an injective module. And the contravariant functor dash B is exact. What else? So again, I'm gonna mention this X group. We'll calculate it shortly. So X I A B is 0 for all I bigger than or equal to 1 and all A. Another thing, there are a lot of X groups. Maybe just like before, it suffices to just calculate one of them. So X, something showed up. Hold on. Okay, X1 A B is equal to 0 for all. Okay. Oh. Okay. So similar to before, but it's curious that X, depending on which, I guess, I mean, it's the same X. I've written the same X, but somehow, depending on which entry you vary, if it's 0 for all A or all B, they characterize injective or projective. It's very curious, and that's kind of what I meant by the symmetry of X. And this will come up later when I show you guys that there are actually two ways to calculate X. They give you the same thing, and it shouldn't be. It is not clear that they should give you the same thing. I'm not going to elaborate, but yeah, it's curious. So you should read about that later. But today we'll just calculate. Okay. Since I'm low on time, I wanted to mention the bare criterion for injective R modules. But maybe I won't. I'll just say that unlike in the case with our projective modules, we actually have sort of a way to determine if an R module is injective by some funny question that we can ask. You should look into that. we're not going to use this bare criterion anytime today, so I think I'm just gonna skip it. And so one corollary that comes about is that so there's this bare criterion for injective R modules. I'll let you read about it. This leads to the corollary that if R is a PID, so remember PID is integral domain where every ideal is generated by one element, right? Does R need to be commutative? I don't think so, but okay. If R is a PID, then an R module A is injective if and only if A is what is called divisible. And A is divisible if for every A in A and R in R, you can find there exists B such that A equals RB. So in quotes, you should write something like A divided by R equals B, right? So that's why it's called divisible, because you can divide by the scalar R.
And we need R to be non-zero, right?
Yes. Yeah. R is non-zero. Yes. Right. Thank you. Yes. Yeah. And so example, so in Z modules, the injective, some injective Z modules are the rationals, and then this funny group I'm going to write down. So Z adjoin 1 over P. So this is just rationals whose denominator is powers of P for a particular prime P. And then by modding up by Z, you should imagine like wrapping it into a circle. So it's like, I like to think of it as like the points on the complex unit circle whose angles are like 2 pi divided by p to the alpha or something like that. And the multiplication is the usual multiplication in C, something like that. But you can form this kind of group for any P. There's another notation for this, which I am not familiar with. ZP infinity. I think this might have to do something. I don't know. Is this like a p-adic notation? I'm not really sure. I've never seen this before. But the result is that any injective Z module is a direct sum of these. Is a direct sum of these. So for example, so Q itself is actually going to be the direct sum over P of CP. Wait, what? No, this should be Q mod Z. Yeah. Okay. So, okay. We mentioned that injective modules were dual to projective modules. There is a meaning to this. What is precisely is going on is that, okay, so so I've defined injective modules. In this definition, you can do it in an abelian category. You can talk about injective objects. And so in an abelian category A, the following happens. So M is, if M is injective in A, that is the same as saying that M is projective in A op. And so, okay, maybe you might object, is A op an abelian category? You check for yourself, it is. So this is what is meant by dual. And we'll come to this in a bit when I talk about how to calculate next. Okay. And so some more terminology. So for an abelian category A, we say that it has enough injectives or projectives if for any M in A, there exists an injection. With an injection, M going into I for some injective object I. And then for projectives, it's the other way around. You want a surjection P going to M for some projective object P. Okay. So now to actually calculate the X groups, and we'll just stick to modules. Why not? I mean, I don't think you need to for any of this discussion, but if it helps, think about modules. Okay. So let's talk about the first way to calculate X I A B using our covariant Hom function. This is Hom A dash. Okay. Okay. So step one, start with an injective resolution of B. So what is that? That is, so this is an exact sequence that looks like this. So it starts from 0 to B, and then you start putting in these injective objects. So I'll put I0, I1, I2, and so on and so forth. So this is a cochain complex, right? And it's also an exact sequence. And in particular, I will denote by this part, this is I upper bullet. Okay. And I mentioned this out loud, but each I is injective or injective object. Injective module. Okay. Cool. Then apply our covariant functor to I bullet. So notice that I don't mean to apply the functor to the entire exact sequence. Just apply to I bullet. You don't have to, but why not? I mean, you can see how you should do it if you want to apply the functor to the entire thing. It's not much different, but okay. So apply dash A, no, other way around. That's the contravariant one. A dash to I bullet to get this cochain complex. So now it no longer is exact, right? Because this Hom functor is only left exact. So something will change. And anyways, this was possibly a lengthy sequence. So what? Yeah. So what do you get? I'll just denote it by f of I bullet here. This is going to be a I0 going to a I1 to a I2, so on and so forth. And maybe now I'll give names to these maps. So this one is D0, this one is D1, this one is D2. And okay, so whenever I have a truncated sort of complex like this, what is meant is, if it's cut off, what I mean is that really there's like a bunch of zeros behind here, but just to aid in visualizing what's going on, I'll just draw the 1 0 behind the first group here. And so now take cohomology to get the X groups. So X I A B is equal to the cohomology, which is HI of this cochain complex F I bullet, which is kernel DI mod image DI minus 1. Okay, so in particular, maybe we should ask, what is X0? This has an interesting answer. So X0 AB, this is the 0th cohomology. So H0 F I bullet. This is, well, it's just kernel, but okay, it's isomorphic to kernel D0, which, okay, now you might ask, what is the kernel of D0? But now we have to remember what we did here with the rest of the complex that I sort of cut off earlier. So because the covariant Hom functor here is left exact, if I just look at maybe these 4 or 5 terms or whatever, just this first part, and I apply the functor to that, then I'll get 0 A B A I0, so on and so forth. And this map is D0. And then this map here is injective, right? Because Hom functor is left exact. So the kernel of D0 is equal to the image of this inclusion, which is Hom A. So that is to say that this is the 0th X group is actually just Hom A B. That's cool. And so now you may wonder, okay, how do I calculate the other X groups? Well, okay, you need to know what these DI maps are. That will depend on how you chose your injective resolution and the maps there. So you need to be able to actually get your hands on an injective resolution to do this. Okay.
I have a question.
Yes.
So we drew this arrow going into Hom from 0 to Hom A I naught. What I0? Why did we? No, above in white next to F of I bullet.
Oh, this one here.
Yeah. What is that? What's happening? Because that's not actually exact, right?
Right. It's not exact. So okay, so let's pretend the 0 isn't there. So I started with this injective resolution, which is exact, right? This whole thing here is exact. When I apply the Hom functor to it, or at least even just to I bullet, I'll get this part here, right? Now this sequence here is possibly not exact anymore, but it is still a cochain complex, meaning I can still compose 2 maps together and get 0. And so I can keep it a cochain complex by putting the 0 here. In fact, the 0 is always there. What I meant was that this I bullet here is really this. And this is a cochain complex. So yeah.
Okay, so we lost the exactness like the moment we applied Hom, so it okay. I see.
Right. So that's when we take cohomology. When you lose exactness, you should ask, how much did I lose? And that's measured by cohomology or homology.
Thank you.
Yes, no problem. Okay, so this is one way to calculate the X groups. Okay.
And so sorry, because of the left exactness of Hom, that's why the green thing is exact.
Right, the green thing is exact, or you get this. Yeah.
Is mom there yet?
We use the exactness of the Hom functor to get this. This part is exact. Well, okay, maybe without the dots. Maybe I can even have one more something here. But point is, the kernel of D0 is the image of the inclusion here by exactness, since Hom functor is left exact.
He was the one that caused all the things.
And is there a convenient way to prove this doesn't depend on the choice of resolution?
That is a great question, Mark. There is a lemma for this. I will not prove that result for you, but it is dependent on the following lemma, which I hope it's coming next in the notes. Yeah, good. It is. It means my notes are well designed. Okay, so good question has been raised. Question. Choice of injective resolution. Doesn't matter. The answer is you can pick whatever injective resolution you like, and you will calculate isomorphic X groups. No matter.
All right, well, listen.
And the reason is due to this comparison lemma that I should write down. You can imagine once I write this down how you would use this to prove the theorem. So comparison. So okay. Given injective resolutions of M and M and a map F from M to N, you can sort of complete the following diagram. So, okay, so let's just draw the injective resolutions of M and N first. So that goes 0 to M, and then maybe this one is with I's. And then for N, you might have something like this. Let's say J. And we have this map from M to N, F. So with this information, I can find maps going like this. What should I call these? I don't know. There just exist maps that you can form by lifting. You can lift F along these inclusions, right? Because M includes into I naught and N includes into J naught. You can keep lifting up F in a particular way and form these maps between the I's and the J's, such that you actually get a chain map. So that is all these squares commute. And maybe you call, okay, so I should write this down. Form lifts to obtain a chain map F tilde maybe. And so this chain map F tilde is unique up to cochain homotopy equivalence. So this is the comparison lemma. And so now how would you start with this lemma to try to prove that calculation of x does not depend on the injective resolution? Just take the identity from m to m and take two different injective resolutions and see, and follow your nose. I will leave you to see what happens, but this is where you would start. But punchline, the choice of injective resolution does not matter. So it is in our interest to find a convenient injective resolution in many cases. But I actually don't know if I've ever done a calculation with an injective resolution. I typically use projective resolutions, and more often actually free resolutions. So we'll see that in the next second way to calculate x. Okay. Second way to calculate x. So use the contravariant Hom functor. So okay, here specifically x I a b. Okay, use contravariant dash b. Okay. So now we have to remember something. So it's contravariant, which is to say it's a functor from R mod op to AB, right? Abelian groups. But because of this op thing, we should start with an injective resolution of A. So okay, start with injective resolution of A in R mod op. This is to say it is actually a projective resolution because everything is opt, everything is flipped, i.e. a projective resolution of A in R mod. Yeah. So what does this look like? Very similar to the injective resolution. But it's like flipped, right? You have something like this, P2, P1, P0, and P0 will surject onto A like this. This is an exact sequence. Projected resolution is this thing. And then like before, maybe I'll just call this chunk of it P bullet. And this is not P upper bullet, maybe it's P lower bullet. P lower bullet. So I should really have these numbers down here. 2, 1, 0. Right, because this here, it's descending, I guess, when you look at it. Okay, so it's a chain complex that is exact. Okay, and then like before, apply the but this time apply the functor, but it's contravariant, so it flips it around. So apply dash b and get okay, well, right. You have to apply it to just P lower bullet and obtain the following. Now it's flipped, so, and I can always prepend by 0 since I'm just having a cochain complex now. 0 P0 B, then P1B, then P2B, and so on and so forth. And at this point, I guess I'll label the maps now. This is now D0, D1. Now it's a cochain complex. Now it goes up because is contravariant, right? So okay. And then like before, now it's possibly not exact. So now calculate cohomology. And what do we get? We get the X groups. So then that's X I A B is equal to H I, what should I call this? This maybe F of P lower bowl. Okay. Okay, and that's per di mod image di -1, like before. And maybe I'm low on time, so you check that x0 AB calculated this way is also still just AB. So I mean, it's really weird. Somehow we stumbled across, you know, if you do this process with two different functors, somehow we get the same x groups. Well, at least just for x0, it is the case that I mean, maybe I should have labeled the first calculation as like x covariant or something, and the other x is x contravariant or something. And there's a theorem to prove, and the theorem is that you actually get the same x groups when you calculate it both ways. That is a theorem. It's not obvious that this should even like get you the same group, but it is the case, and I will not elaborate. It's kind of not easy. There is a way to do it with spectral sequences, which I also probably will not elaborate on, because even just developing the language for spectral sequences will take time. But, you know, if you're interested, read about it. It's cool. Okay. So 10 minutes left. What other remarks can I make? Yeah, so I mentioned that like I don't really calculate with injective resolutions. I guess typically, I mean, at least from my experience, it is typical to use a projective resolution. And even like more specifically, a free resolution. I did like an RU where we had to calculate a bunch of these kinds of groups. Well, not the X groups, but we needed to have projective resolutions. In Macaulay too, if you have a module over like you can ask for, okay, we were doing some algebraic geometry project, but like, so we wanted resolutions of coordinate rings, but like nice simple ones. So it's polynomial ring over C and XY and mod up by some silly relation, something. And that ring is very nice, finally generated, blah, blah, blah. So we asked for you can ask for free resolutions, and the computer can actually calculate these. It's a little amusing. You can even ask for the computer to give you free resolutions over Z mod, like very big prime, very big meaning like 5-digit prime Z, and it will produce something that's worth looking at. It's a little amusing. Macaulay 2 is a lot of fun. You should try it. But yeah, we use free resolutions a lot in practice, I guess. So the second way to calculate is very interesting, and it's nice that it coincides with the other one. Okay. Maybe I should say some properties about X. X to I A B. So you may wonder if this process is functorial. It is. In both components, it is functorial. It's very nice. So so functorial in both components. What else? X distributes. Well, okay, that's maybe not the best word to say, but it respects products, possibly infinite ones in a particular way. So the relations are, so X I of the coproduct of A alpha. So I'm going to use both the product and the coproduct symbol here because these relations are true for possibly infinite coproducts and products. So this, and then B. This thing is isomorphic to prod alpha of X, A alpha B. And then the other one is X I of A with product alpha of B alpha. That's isomorphic to this. It should be I. Yeah. Cool. There are a few more properties, but maybe one thing one fun fact is that X commutes with localization in a particular situation. So localization is a functor, right? So for this to work, we actually need Noetherian R. And you need A to be finitely generated. Curious. I actually did not write down the exact relation for this, but I'm not going to write it down because it's possible I mess it up. But you can Google this phrase and it will come up. This is fun. It's worth proving. I think on an exam I had to prove this. It was a take-home, thankfully, but that was fun. So at the beginning, I hinted that there may be so something like this, right? If you had a short exact sequence, A, B, C, 0, and you apply the Hom functor, you might just get, right? Because it's only left exact, right? So it's Hom AX maybe. You know, whatever, and then it stops at a certain point, and you might wonder, you know, oops, it stops here, and you may wonder if you can append something to it and make this new thing exact at the last node, or the second to last node. Yes, there is, and this is expressed by these two long exact sequences that you get from X for X. So long exact sequences for X. Maybe for time, well, okay, it's a bit of a shame. It's probably unlikely that I'll get to do some calculations, so I'll just yeah, I'll just end off with the long exact sequences for X, and we can calculate a couple X groups tomorrow. So for an SCS, 0 to X to Y to Z to 0. Wow, these are going to be long. Maybe do I cheat and copy from my notes? Okay. 0. Oh, I regret it already. Right, so this is the usual thing you want to see, right? AX, AY. Oh my God. AZ. And then now the interesting part is that you can actually continue this down, and then you will get X1. So, okay, I write X1 because really what's happening is that this is supposed to be X0, but it's like nicer to write like this in some sense because it answers that question from earlier. So X1, AX, and then, okay, X2, or sorry, X1, another X1. Okay, you get the idea. And then there's another one for this. So this is the one for coming from the covariant Hom functor. There's another one for the contravariant one. So this was for Hom A dash, and then the other one. There's another one, which I probably don't have time to write down for the contravariant Hom functor. Yeah. Okay. Yeah, I think I'd rather end 2 minutes early than rush a calculation or anything. But yeah, I'll see you on Friday. I apologize for this weird happenstance. Wrong place at the wrong time, right? Okay. Okay.